We're recording. Right. Okay. That's all right. Hang on. Okay, so if you are in the position where you've done my mechanics videos from Easter, then we have just 3 lessons of syllabus to go. Well, although actually there's the first things we're going to do as revision are a couple of bits and bobs that we didn't really cover. So, for example, differentiation of truth by first principles and bits like that. But yeah, we are on the home run, and we're in quite a privileged position in that our first exam is 6 weeks today. So, you know, we've got a bit of time to spare.
What's the date of the first exam?
So it's Tuesday, the something of June. Yes, thank you. And the timetable is outside on the wall now. But 6 weeks is quite nice because the syllabus is split into sixths, isn't it? We've got 4 sixths of pure, 1 sixth of stats, and 1 sixth of mechanics. So in terms of your personal revision, you could decide to structure the 6 weeks you've got between now and then in that way. However, if, as I hope, you sort of made a bit of a start to your revision over Easter, you maybe focused on pure or something here. So anyway, we've got that Easter revision list that I gave you, which we're going to tick our way through in lessons, and hopefully you're going to tick your way through at home. And I'm hoping that, you know, one way or the other, we'll get through everything there. I would suggest that your practice independently needs to be split 50-50 between practice papers and topic-based stuff. Some of you might prefer, I guess if perhaps you are aspiring to one of the top grades, it may be that you are a bit more biased towards practice papers. If you are a bit less confident, it might be that you are concentrating a bit more on topic-based stuff. But I think that 50-50 split is pretty good. So you've had 9 papers from me now. So I'm looking forward to the first person who comes to me and says, "Can I have some more papers?" Because I will say, absolutely, I'll give you as many as you need. The 2021 set, I will give you more printouts of fairly soon. Well, I say fairly soon, in a couple of weeks. So that's where we are. Anyway, 3 lessons of probability. We've done no probability since GCSE. Beyond binomial probability, but no sort of standard probability questions. So that's what we're going to do over these next 3 lessons. So we're going to start. Sorry, of new book. Sorry, yes. We'll start by talking about Venn diagrams today, and so my title for today is 2 sorts of Venn diagram. 2 sorts of Venn diagram. And we need to meet and revise a bit of notation. And when I say revise, I mean revise since GCSE when we last met it, so it might be a little bit rusty. And there's quite a few terms that we need to learn and use, but it will be not tricky at all. It's quite a nice way to work together. It will be nice.
I know, I'm so excited. I think I'm going to go
Okay. So there are, and I apologise that I haven't given you lots of Venn diagram blanks. If any of you are, would anyone like a whiteboard so they don't have to? They are there if you want. If you want. So here we've got a standard Venn diagram question where we are told about a pack of cards, and we pick a card. A is the event that you pick an ace, and D is the event that the card is a diamond. Now, two sorts of Venn diagram. In this first sort of Venn diagram, we're actually going to put the number of cards in the pack that fit in each of these sections. So, perhaps you don't play cards a lot, so you don't know that there are 13 diamonds in a pack, or 4 aces. But we're going to put 4 numbers in this Venn diagram, because we've got 4 areas, haven't we? 1, 2, 3, 4. So 52 cards in a pack. See if you can put the number of cards that are in these sections, the number of cards that go in each section. We'll then address the notation. I know the notation may be a little bit unusual, but just see if you can put the numbers of cards in each of the 4 sections on that Venn diagram. How many cards are aces? How many cards are diamonds? How many cards are neither? How many cards are both? Okay, so there are 13 diamonds and 4 aces, but there is one card that is both a diamond and an ace. And so that means we don't put a 4 here, we actually put a 3 here, and we don't put a 13 there, we actually put a 12 there. And those numbers add up to 16, and there are 52 cards in the pack altogether. So 52 take away 16 is 36. Yeah, 36. So I've completed my Venn diagram. And you may remember that there is a language and a notation that goes with Venn diagrams. It can feature in 2 ways. So here that we're saying n of A means the number of cards in A. So there are 4 cards in A, there are 4 aces. If you pick a card at random, what's the probability that it's from A? Well, it's 4 out of 52, which simplifies down, but that's the probability of picking a card from A. Okay, 3 bits of notation that are really crucial that we understand, and the difference between these 2 is a common difference. So here we're saying this is in either A or D. The U symbol isn't actually letter U, it's a sort of symbol, but it means union. So I think of that as it's in either. It's all together. So how many cards are there in A and D all together? So either A or D, and it includes the ones that are in both. So we've got 16. 3 plus 1 plus 12. So the probability that we get a card that's in A union D is 16 out of 52, which will also simplify. So that U symbol means either. It's the union. I don't care if it's in that or that, I just want to know if it's in either. The second symbol, the N symbol, means intersection. And intersection means I'm only interested in those that are in both. You're far less likely to get something in both, so the numbers here are going to be smaller. So the number that are both aces and diamonds is just 1. And the probability that you get a card that's an ace and a diamond, 1 out of 52. So my notes haven't been very clear there, but there's a line there. So this means union, and we're talking there about either. It's how many cards are either in that circle or that circle, and it includes the overlap. And this means intersection, which is the overlap itself in both. And then the last means not. So how many cards are not aces? And that means how many numbers are not in my A circle. So it's 48. And so the probability that you get a card that's not an ace, well, that's 48. So the only one in the question I haven't answered is this one. So go on, see if you can write down the probability of that. So part D, there. That's the only one we haven't done as part of my introduction here. So not in A, that's these 48 cards, and also in D, then it's those 12. So the answer is 12 out of 52. Not in A, so it's not the 1 or the 3, but also in D. Intersection means it's got to be in both. So it's outside the A circle, but it's inside the D circle. So that would be 12 out of 52. 12 out of 52. So this is the first sort of Venn diagram. We'll meet the second sort of Venn diagram in a moment. But I now need, I did say there's quite a few sort of terms that I need to sort of share with you, which are terms that you've come across before, but as I say, it's a long time since we did probability of this sort at GCSE. So I want to talk about two sorts of events: mutually exclusive events and independent events. And in each case, I'm going to talk about two events happening, but we can have more than two events. So mutually exclusive events are events that can't both happen. So, I play Pat at tennis. Event A, I win. Event B, Pat wins. Those are mutually exclusive. We can't both win, okay? The real winner might be tennis. It might be a great game of tennis, but we can't both win. So those events are mutually exclusive. Event A, it is raining. Event B, it is sunny. Those two events can both happen at the same time, and we get a lovely rainbow. So those events are not mutually exclusive. If I draw a Venn diagram for mutually exclusive events, it looks like this, doesn't it? There's no overlap. There's no overlap. They can't both happen at the same time. And we could even add a little bit of Venn diagram notation in there. We could say, okay, if they're mutually exclusive, then that's true. That's true. Or if it was the number of elements, then there are no elements that go in there. And there's another bit of notation which is sometimes used, which is this, which I have to say I'm not really sure if it's a Greek letter or not, but this means an empty set. It means that this doesn't exist. There is no concept of A intersection B if we're dealing with mutually exclusive events. It's an empty set. So events can be mutually exclusive or not mutually exclusive. Independent events, though we have sort of talked about independence elsewhere, but independent events are where one event doesn't affect the other. So event A, you fail your eye test in Barnstable. Event B, you crash your car driving home from Barnstable. Those are not independent events, okay? Because if you have failed your eye test, there is an increased probability that you are going to crash your car. So those are not independent events, but we struggled with the other group to come up with an example of independent events in that sort of context. But you buy a lettuce in Tesco in Barnstable, you crash your car on the way home from Barnstable. Those, I assume, are independent events. The presence of a lettuce in your car is not going to increase your chance of crashing unless you are nibbling on the lettuce, in which case maybe you'll be distracted. But the bad news about independent events is that they can both happen at the same time, but also non-independent events can both happen at the same time. So you can't tell by just looking at a Venn diagram. So just by looking at a Venn diagram I can't tell you without doing further calculation whether those are independent events or not. The fact that there's an overlap doesn't mean they're independent. It doesn't mean they are not independent. So we do need, with independent events, a more sophisticated way of testing for that independence. And that allows me to introduce the second sort of Venn diagram. Sorry, because I've come from a different class. So here we've got a different sort of Venn, or we're asked to draw a different sort of Venn diagram. Instead of the number of cards or people that would go in each section, we're going to put the probabilities that go in each section. So in this case, I've got two events where the probability of A is 0.3 and the probability of B is 0.4, and the probability of the overlap, probability they both happen, is 0.25. We'll address this in a minute, but I'm going to get you to draw the Venn diagram first. So just see if you can think about what the Venn diagram will look like. It'll look like this, and there'll be four numbers, bum, 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 but this time those numbers will be probabilities. They'll be 0-point numbers, and we know that all of those numbers will add up to 1, because in any scenario, all of the possible options will always add up to 1. Always start by filling in the overlap. Always start in the middle and work out. I'm going to redraw the circle so I can actually squeeze a number in. And don't forget there'll be a number outside the circles as well. So, James, what am I going to put here? Not. Brilliant. Yeah. Now, just make sure you're clear on why we haven't put 0.3 there. We're told the probability of A is 0.3, but because we've already got 0.25 in the overlap, which is in A, that only needs to be 0.05. So in total, the probability of A is what we're told. And similarly then, we're going to have 0.15 there. And if I add those together, I get 0.4, 0.55, which means that the chance that neither of these things happen is 0.45. That's just making the numbers add up to 1. Now, I know there's another event, so we're going to redraw this in a minute because there's another event. But let's now talk about independence. I can't tell at the moment whether these two events are independent. The fact there's an overlap doesn't show me, that I may well buy a lettuce and have a crash on the way home, but that doesn't mean that one caused the other. They could still be independent. Here's the test for independence. If two events are independent, the probability that they both happen, the overlap, will be the probability of one event happening on its own multiplied by the probability of the other event happening on its own. And you may remember we used that in tree diagrams. When we want to work out the probability at the end of a branch, third lesson this week, tree diagrams, we multiply the two probabilities together. So what happens in this scenario? In this question, the probability of A on its own is 0.3, and the probability of B is 0.4. We're told that in the questions, or we could work it out from the Venn diagrams. The probability of the overlap is 0.25. Is 0.25 what you get if you do 0.3 times 0.4? No, it is not. It does not equal that. So in this case, A and B are not independent. Why is this happening? Well, it must mean that the fact that A has happened has affected this probability. Or maybe it was the other way around, and the fact that this has happened has affected this probability. But whatever, these probabilities are no longer the same because one is affecting the other. They're not independent. So if two events are independent, then that is true. And that will come up, I guarantee it. That comes up every time we see sets of papers somewhere hidden in a question. They either say, show that two events are independent, or, are two events independent? Okay, so we now need to hit the reset button because we've got a third event. We need a fresh Venn diagram with a third circle in it. And we're told that A and C are mutually exclusive. So I'd like you to think about where you're going to put C in your circle. Okay? Sorry, where you're going to put the C circle in your new diagram. A and C are mutually exclusive. B and C have a relationship, but A and C are mutually exclusive. So you need to redraw the diagram, and it may be that you need to change some of these numbers. See if you can finish the question now, picking up with B and C. Now we've got this event C thrown into the mix. I'm on a whiteboard to have a punch with. are told that B and C are independent, so we can use that rule, although it's B and C, not A and B. Just like with a normal Venn diagram, start with the overlap. See if you can work out what the overlap is with the information that we're given. Okay, so I'm hoping that you realise that the probability of C is 0.2, the probability of B is 0.4, and they are independent. So we can use this rule to say, right, the overlap will just be 0.4 times 0.2, the probability of B times the probability of 0.2. We couldn't do that with A and B because we didn't know whether they were independent, and in fact they weren't. But with B and C they are independent, so we can use that rule. So that's going to give us 0.08, so that's my overlap there. Now that means that here I've got 0.12, but I also need to change this value here. Probability of B altogether is 0.4, and I've got a 0.25 and a 0.08 inside that circle at the moment, so that's 0.33, so that's going to be 0.07. And it's also going to change this value here, isn't it? It's going to be 0.12 small, so 0.33. So we've then got some weird and wacky notation. So I'm going to get a colourful pen. So firstly, A and B not happening. So A happening is here, and B not happening is everywhere outside the B circle. So this bit, A and B not happening, both, is that bit there. C happening is here. And the union means either. So that or that. So it's 0.05 added to 0.2. So that's 0.25. So here, A and B not happening. Had to have both. A and B not happening, which is this little bit here. B not happening had to be outside the circle. A not happening, A happening had to be inside the A circle. Unioned with C, which was that, and that includes that bit, even though that wasn't part of the B not happening. So 0.25 is the answer. Page 20, 9 and 10.
So how did you get 0.33?
Have I done that wrong? That adds up to 0.4, 0.45,
.57.
0.57. Oh. Am I doing that wrong then? So yeah, is that 4 3?
Yeah.
Yeah, I got one. Yeah, there we go.
Thank you.
Well done. Yes, sorry, page 29 and 10. Now, I'm really keen to get through as much of the content as possible, so it may be that question 10 is one we do, or I get used to independently. A and B are mutually exclusive, so they're not going to overlap. B and C are independent, so start by working out the overlap between B and C. Use the independence rule to do that. You're going to use the fact that B and C are independent to get the overlap between B and C. Firstly. Lots of ways you could draw this, so I mean, if you've done it differently to me, as long as your A and B don't overlap, and C overlaps with both B and A, then that's fine. getting 0.14 as the overlap between B and C because they're independent. That's the secret to unlocking that. Then it's all hopefully straightforward. So remember, the N means it's got to be in both, and the U means either. I'll give you just a couple of minutes before I go through that one. Number 10 is the next one. Let's try. What's up? Hello. Isn't it? It's such a rare smell these days. Kids smoking all over the place. It's true. Right, can we try and unpick these three questions? So, not in A means everywhere outside the A circle, and not in B means everywhere not inside the B circle. So it's the places that are in both. So not in A and not in B. So it's these two here. They're the only numbers which aren't in the B circle and aren't in the A circle. So that's going to be 0.1. 0. The second one, you've got to do the brackets first, haven't you? So in B and not in C. Okay, so in B and not in C. So that's that. So that's the bracket, and it's that union A. So either that or A. So A is all of that. So I've got 0.55 and 0.21, which is 0.76. And then the last one's this really weird one. Some of you will have already seen this. So A intersection C is this little bit here. So not in A intersection C is everywhere apart from that little bit. Everywhere. Apart from that little bit there. Not in B is everywhere outside the B circle. So the combination of that or that, remember this means either, is everywhere. We don't double count the numbers, it's just we've covered absolutely everywhere with either A intersection C dash or B dash. So that's why the answer to that one is 1. I have to say I think that's a little more convoluted than you're likely to get, but there we go. Now, I want to move on, so I'll just show you the answers to 10, but if you didn't get on to 10 or you were halfway through, please, can you finish that one independently? Because I want to move on to a third type of event. Okay, so if two events are not independent, then we say that they are conditional events. One is conditional on the other. So these are inverse, they are opposite. So actually that arrow is not implying they're the same, they are the opposite of each other. One event is affecting another. So we can no longer say that the probability of A intersection B is the probability of A multiplied by the probability of B. We could say that up here with events that were independent, but if one event is affecting the other, then this will no longer be true, because if this happens, this probability changes, or if this happens, this probability changes. So instead we have the concept of this. So it might be the probability of B was 0.4 until A happens. And then we have the concept of the probability of B given that A has happened. So that notation means the probability of B given that A has happened. And that phrase, or those two words, given that, are words to look out for. In a question, the use of the given that sentence implies that we're dealing with conditional events. If two events are independent, then the probability of B given A is just the probability of B, it doesn't change. But if two events are conditional, then this is no longer the same as the probability of B, it changes in some way. So we're going to spend the rest of this lesson looking at some given that questions. And as well as using Venn diagrams, we're going to use two-way tables. So here is a question that uses this given that notation. We are asked to work out the probability that a student studies science given that they study humanities, and here the probability that they study humanities given the fact that they don't study science. And we're asked to put it in a two-way table. So if we all do the same, that makes it a bit easier. So our two-way table, which you probably, again, we haven't looked at for a long time, you've got students that either study science or don't study science. And you've got students who study humanities or who don't study humanities. And we always have a total row and column as well, giving us our grand total here, which is 75 students. So this is the two-way table that we're being asked to draw up. And there's some numbers in there. So for example, 25 only study humanities. So that means they study humanities, but they don't study science. So they're going to go there. So see if you can fill in the rest of that information, then have a go at thinking about those probability questions. For 2 and 3, I'm going to give you a really easy way of doing it, but I'll wait until you've had a think about the tools I have first. So with the numbers that they've given me, I know that there must be 75 take away 48, 27 students that don't do science. So that means there are 2 that don't do science and don't do humanities. I could have done that by working out that that was 39 and the same thing. So the answer to part 1 in part in B is 2 out of 75. 2 out of 75. Because there are 2 students that don't do science and don't do humanities. That's what we're talking about there. But it's really 2 and 3 that I wanted to talk about, and I said I was going to give you a really nice, easy way of doing it. So what's happened is we picked a student at random, and normally, when you do that, your denominator will be how many students you've got in total. So in this question, it was 2 out of 75, because there were 75 students. But here, we're told something about that student. We're told that they do humanities. So we always start here and say, right, that's going to give me the denominator of my answer, because I'm not dealing here with any student from this 75. I'm only dealing with humanities students. So I'm only worried about those students doing humanities, which is 36. So my denominator is going to be 36. Because I know that I've picked someone from that 36 students. That's what this means. Science, given that they already study humanities. Okay. This, therefore, tells me my numerator, the top of my fraction. Because we're now just looking at these 36 students. Of those 36, how many do science? 11 of them. So it's 11 out of 36. So these given that questions, and sometimes they use the notation, and sometimes they use the words. They are easy if you think about denominator and numerator. See if you can write down the answer to the second one in a similar way. Okay, so S dash is my denominator. I'm only dealing with the students that don't do science. So there's 27 of them. Of those 27, how many do humanities? 25. I can't believe the time is already flown. So let's just look at a couple of questions. Let's look at one where it's wordy. So see if you can, should be straightforward again, it's just the same thing except instead of using this notation, they're doing it in words. But again, think about what it would look like in this form and see if you can do the whole denominator numerator thing. Well, yeah, good question. But hopefully you'll remember it now. I mean, there's 4 sorts, aren't there? 52 divided by 4. But yes, you might say, what if I don't know there's 52 cards? So this is what they're asking, isn't it? What's the probability of A given that D? What's the probability of getting an ace given that the card is a diamond? Well, there are 13 diamonds, one of which is an ace. So I'd be really grateful if you could have a go at question 9 by next lesson, as well as finishing off number 10 on page 20. And we can then move on next lesson apace. I mean, I know with quite a lot of terms and everything, but hopefully it was not too tricky compared with some of